Applications to computer graphics. So we're going to learn about how matrix multiplication can apply to creating computer graphics. And I have a project where you do like a really super basic graphics programming thing. And I included in the lecture notes here, I have my notes on the reading because I am constantly going to be referring to this matrix and this matrix. And so like those are things that you're probably going to excuse me, have on your paper for the test. So the reason those are the matrices that we used is because we just like forced the arithmetic to work. All right, so you'll see it work in a minute. All right, so for the demo, we want to consider this data matrix 0, 1, 0, 0, 1, 0. So that's 3 points all put into one matrix. And I've written them vertically. So the point 0, 1 is right here, and 0, 0, and 1, 0. So I've created a triangle. So there's my graphic. All right, so without using linear algebra, right, I'm just going to sketch the image under the transformation that scales the x-coordinate by 2, then rotates 90 degrees about the origin, and finally translates by 3, 1, which means right 3, up 1. So I'm going to just sketch each of those things separately and then see where it finally lands. All right, so the first thing I'm going to do is scale the x-coordinates by 2. So let's see, I'm going to write 0, 0, 1, 0, and 0, 1. Those are my 3 points, right? So if I scale the x-coordinates by 2, I'm still going to have 0, 0, because 0 times 2 is still 0. And then 1, 0 is going to become 2, 0. And 0, 1 is going to stay 0, 1, because take the x-coordinate of 0 times 2, still 0. All right, so after I scale the x-coordinates by 2, I'm going to have 0, 0, 2, 0, and 0, 1. So this is my new triangle. Scaled the x-coordinates by 2. Then I'm going to rotate that triangle 90 degrees about the origin. So it's going to flip up. So I'm just going to say, okay, where does 0, 0 land if you rotate it 90 degrees about the origin? It stays at 0, 0. 2, 0, if you rotate that 90 degrees, it's going to land at 0, 2. And 0, 1, rotate 90 degrees, it's going to land at negative 1, 0. All right, so let's see, new color, I'll plot those points. I have 0, 0, 0, 2, and negative 1, 0. There's my triangle. It's been x-coordinate scaled by 2, then rotated 90 degrees about the origin. All right, finally, translate it by 3, 1. So that means move it right 3 and up 1. So 0, 0 is going to go to 3, 1. 0, 2 is going to go to 3, 3. And negative 1, 0 is going to go to 2, 1. Just add 3 to the x's and 1 to the y's. So my final triangle is going to be at 3, 1, 3, 3, 2, 1. So that's my final one. Sketched. I took my original triangle. I had to sketch a whole bunch of stuff, but I figured out where it landed. Now I'm going to use multiplication by a 3 by 3 matrix to find the image of the data under those same 3 transformations. I'm going to use linear algebra to find out where they land instead of visualization. Okay, so here's the weird thing about this is that you have to work, because the multiplication is not commutative, you have to work right to left. So you start by creating your data matrix, which was 0, 1, 0, 0, and 1, 0. Those are my 3 data points. And then I make them homogeneous coordinates. I just add some 1s on the bottom. Okay. And the reason is that we just have to do this to make the algebra work, Like, we're still working in a plane. It's just not the XY plane. It's got Z coordinates that are always 1. So we're still working in 2 dimensions, but we have to use 3 by 3 matrices in order to make the translations work. All right, so this is my data matrix. Just has my data points in it. And then the first thing I'm supposed to do is scale the X coordinate by 2. That was my green triangle here. So in green, I have to put down a matrix that scales the X coordinate by 2. Okay, so the way you do the scaling and the rotating is you always have this like L zeros with a 1 in the corner. And then what you put in the 2 by 2 that remains is the standard matrix for a T that does that transformation. Okay, so T is a transformation that scales the X coordinate by 2. So underneath here, I'm going to figure out, if you remember how to find the standard matrix of a transformation, you have to know where like T of E1 goes and T of E2 goes. So T of E1, that's T of 1, 0, scaling the X coordinate by 2, so it's going to go to 2, 0. And then T of E2, that's T of 0, 1. So that's going to stay at 0, 1 because you're scaling the X coordinate by 2. So 2, 0, and 0, 1, that's the standard matrix for this transformation. Those are the columns of the remaining 2 by 2 spot in this matrix. So I have 2, 0, and 0, 1. All right, so I'm working right to left, and I know that it's weird, but it's because you have to multiply your data matrix by the matrix that scales by 2, and the order matters, and you have to do it on the left. So you kind of work right to left. All right, so my next one is the purple. That's the rotate 90 degrees. All right, so I'm going to do this. My next matrix is my rotation 90 degrees about the origin. So I just need to know, where does 1, 0 go and where does 0, 1 go? So the point 1, 0, just going to draw a quick picture. If you rotate 90 degrees about the origin, it lands at 0, 1. And 0, 1, rotate 90 degrees about the origin, it lands at -1, 0. So in my rotation matrix, I put in my L, 0, 0, 1, 0, 0. And in the remaining 2 by 2, these are the columns, the places where T goes. So you've got 0, 1, and -1, 0. All right, and then the last thing is the translation by 3, 1. So translations work differently. They don't have the 0, 1, L thing. They do have a different rule. And it is, you put 1s on the diagonal, 1, 1, 1. Put 0s everywhere else. And then in these last 2 spots, you put the translation. So you want to go by 3, 1. So this is my translate by 3, 1. And you don't have to do any like calculation of what T does. You just throw the translation into that matrix. So let's see, if I actually check on the calculator, if I multiply these 3 matrices together times my data matrix, I should get what I got earlier, which was these 3 points, right? I should get this. as my 3 points. Although the order is going to be different because I put the order in the data matrix different. Yeah, but I should get those 3 points. So let's pull up a calculator and make it do it. Make sure it works. All right, so 3 by 3. I'll put in the translation matrix first. 0, -1, 0, 0, 0. Oh, you're right, because I'm covering the translation. Thanks. I was like, no, I'm not. 1, 0, 3. Oops. 0, 3, 0, 1, 1, and 0, 0, 1. Okay, so I've got a translation matrix. Edit matrix B, and I'm going to put in the rotation matrix. Oops. Edit B. 3 by 3. Matrix C is going to be a 3 by 3, my scaling matrix. And then lastly, I'm going to put in D, which is my data matrix. Okay, got them all. Now I'm just going to multiply A times B times C times D. All right, so I get 2, 1, 1, 3, 1, 1, 3, 3, 1. And those are the points where I landed when I did it visually. 2, 1, 3, 1, and 3, 3. Right? 2, 1, 3, 1, and 3, 3. Yeah, and the 1, 1, 1s at the bottom are just a placeholder. We need them to make this linear algebra multiplication work. So I'll show you briefly why we need them. So what happens is it's because of the translation that we need the homogeneous coordinates. If it weren't for translations, we could do rotations and scalings just in 2 by 2 world, but it's the translation that makes us need that. And so if I have some data here, x, y, 1, and if I multiply it by hk 1, 1, 0, 0, 0, 1, 0, I want to see what comes out. So you multiply your first row times your vector. So you have 1 times x plus 0 times y plus h times 1. That's how you get your x plus h. You need this 1 here to multiply by the h so that when you add it together, you get the x plus h translation. And then my next row, you have 0 times x plus 1 times y plus k times 1, which is y plus k. And then your last row, 0 times x plus 0 times y plus 1 times 1 is 1. So we just built that matrix to force the answer to give you, instead of xy as your output, x plus h, y plus k, so that it translates by hk. So somebody just very cleverly was like, I can make a matrix that forces it to come out if I just need this extra row here, and it'll work. I'm still working in 2 dimensions. It's just that I have a 1 placeholder in Z instead of a nothing. All right, that was it for that. All right, and then the other thing, That's part of this computer graphics section, though it's not part of your project, this particular thing. This is projection. So it's called the perspective projection. And this is how you program like a 3D model onto a computer screen, right? Like if you want to look at a 3D molecule on a 2D screen, you need to be able to like rotate it and look at all the sides of it. And this is how we create that 3D picture on a 2D screen. So what happens is, before I start getting into the math of it, the way you program it is, if this is my computer screen, I have like my three-dimensional object in front of me, and I'm sitting at the screen and I look at my 3D object, and for each important point on the 3D object, you draw a line from your eyes to the screen, and that's how you like translate it into a 2D picture. So all your important points get translated into 2 dimensions by drawing a line from your eyes through the important point on your 3D object onto your 2-dimensional screen. And then you figure out the coordinates by similar triangles, right? And then they use similar triangles to create some nice easy formulas that you can just remember. But it's all similar triangles like your basic high school geometry. Like if you know the 3D coordinates of this point and you draw a line through it onto 2 dimensions, you can use similar triangles to figure out where it lands. So we have this nice formula for a projection matrix. Which looks like 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, negative 1 over d, 0, 0, 0, 1. D is the distance of the viewer from the computer screen, or the eye of the viewer. That's how far it is from the 2D thing. So then you multiply that times your data matrix. Matrix, okay. All right, so my data matrix, 7, 3, negative 5 is one of my points in 3D world, and I want to project it onto a 2D screen. So we also use homogeneous coordinates for this, so you have to throw 1s onto the bottom of everything. Then I have 12, 8, 2, 1, and 1, 2, 1, 1. And in my projection matrix, my center of projection is at 10. So this just becomes, instead of negative 1 over d, it's negative 1 over 10. All right, so we actually just can have a calculator do this multiplication for me. This is 4 by 4 times a 4 by 3. So my result is going to be 4 by 3. Why is my result a 3 by 3? Oh no. Okay, so when I just did this on a calculator and I get 7, 3, 0, 1.5, 12, 8, 0.8, and 1, 2, 0.9. Now, the problem here is that I need 1s on the bottom. Like that bottom row is supposed to be just a placeholder. So to make them 1s, I divide each column by its last entry. Okay, so I'm just going to divide each entry in the column by its last entry. So this becomes, it's not equal, but it becomes 7 over 1.5, 3 over 1.5, 0 over 1.5, and then 1.5 over 1.5 will make that placeholder of a 1. And 12, 8, 12 over 0.8, 8 over 0.8, 2 over 0.8, 0.8 over 0.8, and then 10 over 9, 20 over 9, 0 over 9. Oops. Sorry. 1 over point, it was 0.9. I was looking at the wrong matrix. 1 over 0.9, 2 over 0.9, 0 over 0.9, and 0.9 over 0.9. And I was just writing down the simplified version of that column. So then simplify. 7 over 1.5 simplifies to 14/3. Then 2, 0, 1. 12 over 0.8 reduces to 5. 8 over 0.8 is 10. 2 over yeah, 15. Yeah. Typo in my notes. 8 over 0.8 is 10. Yep. And then that's a 0. Yeah. 0 over 0.8 is 0. 0.8 over 0.8 is 1. And then I have 10 over 9, 20 over 9, 0, and 1. All right, so it does come out to 2D coordinates. So the ones were placeholders in 3 dimensions. I had to add a 4th row for my 3-dimensional coordinates. Once I do this all, I get 2D coordinates. These are the points that I would plot in the 2D plane that corresponds to the 3D coordinates of my 3-dimensional thing.